Welcome students to this session on operations research. In this session, we will discuss about assignment problems. What are assignment problems? What are the applications of assignment problem and how the Hungarian method can be applied to solve assignment problems? An assignment problem is a particular case of transportation problem where the objective is to assign a number of resources such as human resource, machines, etc. to an equal number of activities or tasks or jobs so as to minimize the total cost or maximize the total profit. The applications of assignment techniques may be useful in, say, the assignment of workers on machines or the assignment of workers to machines, different salesmen to different sales territories or districts, different places, assignment of vehicles to specific routes. The objective remains the same, either to minimize the cost or maximize the output or the profit. One feature of assignment problems is each resource is assigned to only one job and each job requires only one resource of varying degree of efficiency. That is, all resources or every resource, each resource will be assigned to only one job and each job will require only one resource for the different degrees of efficiency. Unlike transportation method where you could split the supply between different customers, here the assignment problems, the assignment is on 1:1 basis. One worker to one job. One worker will get only one job. Similarly, one job can be done only by one worker. So we can say that an assignment problem is a degenerate type of a transportation problem, because you have seen in transportation problems degeneracy occurs when the number of filled cells is equal to m plus n minus, when the condition of the number of filled cells is not equal to m plus n minus 1 condition. Degeneracy occurs in transportation problems when the number of filled cells is not equal to m plus n minus 1 condition. M is the number of rows, n is the number of columns. So whenever the number of filled cells is equal to m plus n minus 1 condition, m is the number of rows and n is the number of columns, we say the solution is non-degenerate. But degeneracy we have seen in some of the previous videos when we were discussing about transportation problems. Whenever the number of filled cells, the allocations in a transportation problem equals m plus n minus 1 condition, then it is not degenerate. But when the number of filled cells is not equal to m plus n minus 1 condition, then we say it's a degenerate problem. And we also seen how to solve a degenerate problem. Here in assignment problem, since your assignment is on 1:1 basis, so you will get exactly 4 assignments. If there are, say, 4 rows and 4 columns, that is 4 jobs, 4 workers and 4 jobs, then your number of rows become 4, number of columns also is 4. So we say the matrix, the order of the matrix is 4. So number of rows is equal to number of columns is equal to the order of the matrix, assignment matrix. So the assignments here will be on 1:1 basis, means the number of assignments will be 4, which is exactly equal to the number of rows or columns. So it will not satisfy the condition of the number of filled cells is equal to m plus n minus 1 condition. It will not satisfy. So an assignment problem is considered as a highly degenerate type of transportation problem. Well, let us see what assignment problem is and how do we apply the Hungarian method to solve this assignment problem. Let us take a problem here, a minimization problem, and solve this assignment problem. In this problem, you can see there are 4 rows here, that is 4 rows represented by 4 workers. So these are the resources which you are talking about. There are 4 workers, worker 1, worker 2, worker 3 and worker 4, and 4 jobs, job 1, job 2, job 3 and job 4. And all these numbers here represent the time that a particular worker takes on a particular job, or let us say these are the costs. Let us assume that these are the costs. So worker 1, if assigned to job 1, will incur a cost of 10 rupees to the company. Worker 1, if assigned job 2, will incur a cost of 15 rupees for the company. Similarly, worker 2, if assigned to job 3, will incur a cost of 28 rupees to the company, and so on. So these are all the cost elements of assigning a particular worker to a particular job. So worker 4, say, if assigned job 4, will cost 18 rupees for the company. Now the first step in any assignment problem is to check whether the number of rows and columns are equal. If so, then we can say that the problem is balanced. So here you can see there are 4 workers, 4 jobs, 4 rows and 4 columns. So hence it is a balanced problem. We have seen in transportation problems, whether it is balanced or unbalanced was not determined by the number of rows or number of columns. In transportation problems, it was total supply. If total supply is equal to total demand, then it was a balanced problem, irrespective of number of rows and columns. Whereas in assignment problem, the one condition that you have to see is whether the number of rows and number of columns are equal. If they are equal, then it is a balanced problem. That is again one more difference between transportation and assignment problems. So when you now look at this particular table here, and you have to now assign each worker to each job, one job. So one worker, one job. So all 4 workers will have one job and different jobs. Same job cannot be shared by more than one worker. Similarly, one worker cannot have more than one job. Same job cannot have 2 workers working on it. Similarly, every worker will have only one job, cannot do 2 jobs at a time. So in the end, there should be 1:1 allocation, one worker, one job, different combinations. Your objective now is to find out which is the best possible combination of worker and job, which worker to be assigned which job, so as to minimize the total assignment cost. So this is minimization, so we are considering all this as costs. Now, if it was maximization here, we would consider all this as profits or the output, or if it's the other way around also, you can look at it. So if this is given as costs, then the problem is minimization. If these elements are all given as profits, then the problem is objective is to maximize. So let us see how we apply this Hungarian method. So the first step in Hungarian method is to find, as we told already, as we understood, whether the problem is balanced or not. In this case, the problem is balanced. Number of rows is equal to number of columns, and the order of the matrix here is 4, because the number of rows is 4, number of columns is 4, so the order of the matrix is also 4. The order of the matrix here is 4. Let us now apply the row reduction. Second step now. After you have found out whether the problem is balanced or not, next step is called the row reduction. Let us see what the row reduction process is. In row reduction, you will first find out for each row which is the minimum element. If you look at this table, for the first row, 10 is the minimum. So you will subtract this 10 from all other elements in that particular row. You subtract the minimum element, which is 10. This is the minimum. So subtract this minimum element from all other elements in that particular row. So 10 is the minimum. So you are subtracting now all the elements in that first row with 10. When we go to the second row, the minimum here is this 10. So again, you subtract all elements by 10. Subtract all elements by 10, the minimum element in this row. Third row, the minimum is 12, so subtract all elements by 12. Similarly, when you go to the fourth row, the minimum is 9, so you will subtract this minimum element 9 from all other elements in the row. So this particular exercise or procedure is called the row reduction. Because you are now reducing the row now. Row reduction. You are now doing the row reduction. So what will be the resulting table now? What will be the new table now after doing the row reduction? You have now substituted every element by the row minimum in that particular row. So your new element or your new table will be you can see here the first, after the balancing part is over, after ascertaining whether it's a balanced problem or not, you have done row reduction now, subtracted the least element of each row from all the elements of their respective row. You have got the row reduction table, and this is the resulting table here. Now next step is to, based on this table which you get by row reduction, you have to now apply column reduction to this table, the new table got by row reduction. In this, find out the minimum element in each column. The minimum element in the first column is 0. So 0 minus 0, 6 minus 0, 0 minus. So you are doing now column reduction. Similarly, when I look at the second column now, 5 is the minimum. So 5 minus 5, 10 minus 5, 6 minus 5. Similarly, 15 minus 5. Third column, 14 is the minimum. So 14 minus 14, 18 minus 14, 18 minus 14, 23 minus 14. Similarly, fourth, 0 is the minimum here. So whenever there is a 0 in a column and you are doing column reduction, the new elements will not change because the minimum is 0. So whenever you subtract something by 0, the original elements remain. Okay. So you have now subtracted now or done the column reduction on the table which you got by row reduction. Whatever you get after row reduction on that table, you have to conduct the column reduction, and then the new table this will be your column reduction table, what you get by column reduction. See here, subtract the least element of each column from all elements of the respective. You have already done that. You have got the column reduction table. So now in this particular table, you have to now cover all these zeros. You have to introduce only vertical or horizontal lines, straight lines, and cover all the zeros in this particular table. You would like to now assign to a place where there is a zero value, but there are many zero values. To find out how many assignments we can make. Can we make an assignment of one worker to one job? Can all workers be assigned to all jobs? That is what we are checking now. So one way of checking it by Hungarian method is to find out what is the minimum number of lines required to cover all the zeros. Minimum number of lines. Minimum number of lines required to cover all the zeros. See, you can now cover it in many ways. You can cover, see, this zero this way. You can cover this by just putting a horizontal line like this, the second one like this, the third one like this, four. So four, by drawing four horizontal lines, you can cover all the zeros. This is one. Or you can do it this way. Erase. You can cover all the zeros by drawing four vertical lines. This is also possible. All zeros are covered. Possible. But the condition is you have to cover all the zeros here with minimum number of vertical or horizontal lines, or a combination of both. Minimum. Now, so you have to now see whether all these zeros now can be covered by three lines. Is it possible? By four lines it is possible. Now check whether all these zeros can be now covered by three lines. Yes, it is possible. Let us see how. See, you can see here the minimum number of lines. All the zeros are covered by only three lines now. So, if the minimum number of lines required to cover all the zeros here is 3, which is less than the order of the matrix. Now you can see here the order of the matrix was 4, number of rows or number of columns, and the minimum number of lines required to cover all zeros is 3. So optimality is not reached. Even though we could cover all the zeros by 4, there was a possibility of covering all zeros by 3. So you have to consider 3. You have to consider the minimum possible number of lines. So 3 is possible. So you have to cover all the zeros by 3, not 4 lines. So in that case, it's not an optimal solution, because the minimum number of lines required to cover all zeros is 3, which is less than the order of the matrix, which is 4. 4 number of rows are there, 4 workers, 4 workers and 4 jobs. So it's a 4 into 4 matrix. So the order of the matrix is 4. So this is not optimal solution. This is not an optimal solution. So now what do we do now? This is not an optimal solution. So what we do? The minimum number of lines required, since it is 3 to cover all zeros, and the order of the matrix is 4, optimality is not reached. So you have to now apply, or you have to now remodify the table again. So you have to keep on remodifying or modifying the table. You have to keep on modifying the table now till you can cover all the zeros with 4 number of lines, minimum number. When it is not possible at all, you should reach a stage where it is not possible to cover all zeros by anything less than the order of the matrix. Then you can say optimality is reached, which means till you can cover all the zeros by 3 number of lines, optimality is not reached. So you have to now reconstruct the table, modify the table now, and see to it that optimality is reached. What is the condition for optimality? The minimum number of lines required to cover all zeros should be equal to 4. Minimum number. So let us see how we can do that. The first thing that you have to see here is, just see the table. Looking at the table now, find out which is the least uncovered element. You can see here some of the numbers are covered by lines, some are not. For example, this 1, 4, this 4, this 10, this 9 and this 9, they are not covered by any lines. So find out which is the least uncovered element. So in this case, the least uncovered element is this 1. So what you will do now, subtract this least uncovered element from all other uncovered elements. Subtract this one from all other uncovered elements. So this minimum uncovered element was 1. So you are subtracting that now from all other uncovered elements. So in the new table, at this position, you will get new values which will be equal to 1 minus 1, 4 minus 1, here again 4 minus 1, 10 minus 1, 9 minus 1 and 9 minus 1. So subtract the minimum uncovered element from all other uncovered elements. Add that minimum element of 1 to that element where two lines are passing. That is, wherever elements are lying at the intersection of two lines. You can see here this 0 is lying at the intersection of a horizontal and a vertical line. Similarly, this 6 is lying at the intersection of a horizontal and a vertical line. So add 1 to that particular element. Add 1 to that particular element because that is a minimum. So this minimum uncovered element, you are now adding to the point where there are elements which lie at the intersection of two lines, Now wherever there are numbers where only a single line is passing, for example this 0, this 20, this 5, 4, 0, this 0, this 0, all these numbers where only one line is passing, that will remain as it is. That will remain as it is in the new table. So please keep in mind what you have to do. Just look at the table that you have got after column reduction. See what is the minimum number of lines required to cover all the zeros. Now in this case you have got minimum number of lines is 3. So now take or check the least uncovered element, subtract that least uncovered element from all other uncovered elements, add that least element to the intersection point elements, and all other elements through which single line passes will remain the same. This is what is told to you now. Just look. The least element not covered by any line is 1 in the previous table. Subtract 1 from all the elements not covered by the lines and add 1 to the elements, so the points of intersection of the lines. All elements through which a single line passes will remain the same. So as a result of that, you have now got a new table. When you have done all this, you get a new table. This table you have got, that is the modified table. This is the modified table. This will be your modified table. This is your modified table. Now looking at the table here, the modified table, just look at the modified table here. You can see all these changes have been made now, and again try to fit in the lines using horizontal and vertical lines. Try to cover all the zeros now. You can now get exactly 4 lines. You cannot get a better solution. You cannot cover all the zeros now by 3 number of lines now. Just check. All of you can try this. The minimum number of lines required to cover all zeros now is 4. So you can say that an optimal solution is reached. So in the new table now, the minimum number of lines required to cover all the zeros. Only horizontal and vertical lines you have to draw. In this particular new modified table, after you have applied all this, after you have applied all these rules, this one, least element not covered by any line is 1, subtract 1 from all elements not covered by the lines and add 1 to the elements at the point of intersection of horizontal and vertical lines. All elements through which a single line passes will remain the same. So based on that, you have got now this particular modified table, and in that table again now cover all zeros by minimum number of lines. So the minimum number of lines required here will be 4. That is the minimum, and since this 4 is equal to the order of the matrix, we say an optimal solution is reached. We can say that an optimal solution is reached here. An optimal solution is reached. Now we have now seen that an optimal solution is reached. But now we have to now assign the worker a particular job. Each job has to be now assigned to each worker. So how do you do the assignment? Let us see. Now that the optimality condition is confirmed, because the minimum number of lines required to cover all zeros is equal to the order of the matrix, which is equal to 4. Let us now make the assignments. Let us examine each of the rows. For example, if we take the first row now, there are two zeros here, one zero pertaining to job 2, another 0 pertaining to job 3. So you have to now assign to that cell which has a 0. But you have to see that all the workers have been assigned one particular job. So it is to be 1:1 basis. On a 1:1 basis, assignments have to be made on 1:1 basis. So the worker 1 will now be assigned to which of this? There are two jobs here with 0 value. So whenever there is a row where you have two zeros, wait. Go to the next row. When you go to the next row and see, for worker 2 you can see here there is only one 0 here corresponding to job 4. So immediately box that, which means you are now making a assignment, that is worker 2. You are assigning job 4 to worker 2, because you can see here there is only one 0 value here in this second row. So immediately job 4 is now assigned to worker 2. Job 4 is now assigned to worker 2. Go to the third row now. When we go to the third row, again there are two 0 values. Two 0 values here. We'll wait now. Go to the next row, worker 4. In this particular row, fourth row, there is only one 0 value here. So immediately you will select that. You will select that. That means worker 4 will be assigned job 1. Worker 4 will be assigned job 1. So job 1 is now assigned to worker 4. Worker 4. Now let us see the columns now. If you go to the columns, if I see the second column, you see the first column and the fourth column are already assigned. Both these jobs are assigned, job 1 and job 4. If I see job 2 here, there are two zeros here. You can see there is a 0, there is a 0 here. Leave that. Move to the next one, job 3, third column. In this column there is only one 0. So immediately assign it to worker 1. So worker 1 will be assigned job 3. Job 3. So job 3 is assigned, worker is also utilized. What is left now? Worker 3 and job 2. So this 0, this job 2 will now be assigned to worker 3. Job 2 will be now assigned to worker 3 will get job 2. Worker 3 will get job 2. So this is your optimal assignment. This assignment will give you an optimal value. You can just check. Worker 1 will get job 3, worker 2 will get job 4, worker 3 will get job 2, and worker 4 will get job 1. So your final allocations in the original assignment table will be worker 1 job 3, so 24, that is cost is 24. So if worker 1 is assigned to job 3, 24 rupees is the cost. Refer your original assignment table, the first table that was given to you initially. Worker 2 to job 4, 10 rupees, worker 3 to job 2, 18, and worker 4 to job 1, 9. So when you add up all this, it adds up to 61. So the total cost optimal is 24 plus 10 plus 18 plus 9, that is 61 rupees. So this is your final assignment. So your Z value here, or the total Z value, or the minimum cost, optimal cost for this assignment problem will be rupees 61. And the assignments as given here, worker 1 to job 3, worker 2 to job 4, worker 3 to job 2 and worker 4 to job 1. So this is the solution for the problem. In our next video, we will discuss about the same Hungarian method of solving assignment problems, but we'll consider an unbalanced problem where the number of rows is not equal to number of columns and see how we can solve it applying Hungarian method. Thank you.